Okay, so here we have our lecture on the properties of water, and water is most definitely the most versatile molecule on Earth. This is a list of objectives. These are things that you should be able to answer or understand by the end of the video lecture. If you're still having trouble, remember consult additional resources, or you can contact the teacher and ask for help there as well. So, water everywhere. Water covers about 3/4 of the Earth. You can see its lovely blue hue from outer space. It makes up roughly 50 to 95% of the composition of living things. For humans, we're pretty close to the 70% mark. Some animals or some organisms are made of more water and some are made of less, but there is a threshold. All organisms are made of water in some way. When we look at the importance of water, well, here's a great statistic that shows you. Humans can survive for about 3 weeks without water, without food, but they will only last for about 3 days without water. The molecule, let's break this down. Water is H2O, so there are 2 hydrogen atoms and 1 oxygen atom. We know that when atoms form relationships with each other, these are called bonds, and those bonds are due to the interactions of the electrons in the atom, and this is a review from middle school. One way that we can form bonds is a covalent bond, and that is when electrons are shared between atoms. So here we see the hydrogen atom and the second hydrogen atom, and then this big guy here is the oxygen atom. Okay, obviously the oxygen atom is much larger. It has more mass and it has more electrons, protons, and neutrons compared to a hydrogen atom. So when we look at the sharing here, oxygen says, boy, I'd really like to have this part of my atom feel whole. And it says, why don't we share the electron that you have? Hydrogen only has 1 electron. And so what we get is this interaction right here where the 2 atoms are going to share an electron. Now oxygen does this with 2 hydrogen atoms, so we're going to share here as well. Okay, so both hydrogen atoms are sharing. Even though there are the electrons being shared between the 2 atoms, there is no change in charge. Okay, there's an equal charge here, and let me just show you what I mean by this. Let's see, let's get red off of here. Black. Okay. So when we look at the charge of a molecule, we have to add up the protons and we have to add up the the protons and the electrons. So we have 8 here in the oxygen atom for protons, and then +1 and +1 from the hydrogen. That gives us 10 protons. Okay? So those are 10 positive things. In order to have a neutral charge, that means we would need to have 10 negative things as well. Positive 10 plus a negative 10 equals 0. So let's double check. All these yellow dots, these represent our electrons. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, 10 electrons as well. So therefore our charge is going to be neutral. Okay, and that's very important. So the overall molecule has a neutral charge. However, it feels and it acts like it has a charge, and that's because water is what we call a polar molecule. When you think about the poles of the Earth, this poling of one extreme to another, polarity refers to the unequal distribution of charge within a molecule. So let's break this down. Here's what this means. And on your slides, the next slide, I have a much larger picture for you so you can see the diagram a little bit more clearly. Okay? You can follow along there. That's fine. So here we have our hydrogen atom, our other hydrogen atom, and our oxygen atom. All right? And when we look at the concentration of electrons, we see all of the electrons are sort of more on the oxygen side than on the hydrogen side. And that's what's going to happen there is it's going to make this half of the molecule, right, if we divided a line, we said this side, it feels more negative. It has a negative pull to it, all right? And so we would say it's not that it has a negative charge, no, but rather that it feels negative. So that's why we put these parentheses around it. So not a negative charge, but it just feels more negative on this side. And then when we look at the hydrogen, since all the electrons are gathered over here on this side sort of feels a little bit more positive. All right, not a positive charge, but a positive pull. So remember, overall, the molecule is neutral in charge because it has a balance of electrons and protons. But the way that they are organized within the molecule, one side of it feels more negative than the other side. It's very imbalanced in a way. So more electrons are drawn to the side where the oxygen atom is, and that gives that side of the molecule a negative feel. More of the positive side is left for where the hydrogen atoms are, and that gives it a more positive feel. This is a really important concept because it produces a lot of water properties. All right, here's the diagram that I gave you. All right, one of the properties is hydrogen bonding can occur. A hydrogen bond occurs between water molecules. So in this diagram, it's all the light blue dots that are connecting in between. Notice what are being attracted to one another. It is the oxygen of one atom, of one molecule of water, and the hydrogen of another molecule of water. So when we look at that and we think about polarity, what did that oxygen feel like? Oh yeah, it felt kind of negative, right? And then this hydrogen had a positive feel, right? So why is there a bond that is forming temporarily between the negative feeling of oxygen and the positive feeling of hydrogen? Opposites attract, right? And that's something you've learned in school before. Opposites attract. So you have the negative part of one oxygen being attracted to the positive part of the hydrogen. And this is occurring between different water molecules. So it's really important that you understand the difference between a hydrogen bond and the covalent bond. So a hydrogen bond is right here, and it's occurring between two different water molecules. Whereas the covalent bond, that's what holds a hydrogen atom to an oxygen atom. Okay, and that is within one water molecule. So because of the fact that we have this polarity and the ability to form hydrogen bonds, we get these beautiful properties of water which make all of life on Earth possible. Property number one, water can be sticky. Okay, and when you think of sticky, you think of like tape, right? So water has the ability to be cohesive, and cohesion means that a water molecule sticks to another water molecule. So when we look at this drawing, again, you see those hydrogen bonds holding this molecule to this molecule. Well, we can create a whole network of these, and that produces some very interesting effects. For example, have you ever tried to pour a glass that was just too full and you poured it too slowly? Okay, water molecules are going to stick together to keep that stream of water all together. Another property that makes water sticky is adhesion. Water is able to stick to the surface. So when you're pouring that water out, it's trying to leave the surface of the glass, but it's attracted to the surface of the glass, and so it stays stuck to it. And that's usually when you're trying to pour into something that's over here, but instead the water dribbles down the edge of the glass, and usually like on your pants or something. So water is sticky. It could stick to itself, cohesion, together to each other, or adhesion, it can stick to something else. All right. Why is this important? Well, because water can stick to itself, it can form long chains of water molecules, and that's going to be important in how plants are able to move water from where they absorb it in their roots all the way up against gravity to, the leaves and out to the shoots. In addition to that, because water is sticky, okay, cohesion and adhesion, it almost turns it from being a fluid into a solid. And so we get this unique property called surface tension, and that allows water to have some tension. In other words, it acts sort of like a solid in a way. And we can see that demonstrated here with this water strider bug. Here, this insect is able to walk across the top of the water because those water molecules are sticking so strongly to one another that they're resisting being broken through by the body of the water strider insect. Okay, property number 2. Water is a versatile solvent. Okay, so introduce some terminology here. When you have a solution, let's say you pour some salt into water. The solute is the substance that is dissolved, and so in this case that would be the salt, whereas the solvent is going to be the substance which is doing the dissolving, and that is going to be the water. And what do we mean by dissolve? So when something dissolves in water, that means that it is going to break apart, is going to dissociate or come apart into pieces because it gets along well with water. And that's why we use the phrase like dissolves like. So a polar molecule like water gets along well with other polar molecules, whereas a nonpolar molecule gets along well with other nonpolar molecules. So what happens when you mix a polar and a nonpolar molecule? Well, if you try and do that, you're going to get a resistance. And I'm sure you've seen this if you have taken water, a very polar molecule, and you add oil to it, which is nonpolar. Do the two mix very well? No, not at all. The oil sort of globs together and stays as separate as it can from the water. It's very water-fearing, or what we say, hydrophobic. Okay, here's a term that you might want to know, hydrophobic. And what that means, let me just, right here. That means water, I gotta work on my handwriting, right? Water fearing. There you go. Okay. So in plants, for example, you feel that waxy surface, they're going to repel water, and it's going to sort of bead up because the water molecules will be attracted to each other and they will repel the waxy surface. So they're going to separate. As you can see here, all the water molecules are sort of on their own, and then in the center you have all of the hydrophobic molecules. They're trying to stay very close to one another because they don't like the water. They're like, ew, get away from me. Salt, on the other hand, is hydrophilic. Okay, so if hydrophobic means water-fearing, hydrophilic means loving, water-loving. Okay, so because of that, salt is a polar molecule, water is a polar molecule, so salt will dissolve in water. And what that means is we can break salt down into its pieces. So here you see we broke salt into a sodium ion and a chlorine ion, because that's how salt can separate, and that's what allows it to dissolve into a solution. Another property, water has a very high specific heat, and what that means is the specific heat of a substance is how much heat is gained or lost when temperature is changed around it. And lucky for us, water responds relatively stable to changes in temperature. And here's what that means. Okay, I have an amount of water and I have the same amount of soil, okay, not water. And I'm going to add energy in the form of heat, all right, to both of these situations. So then after I've added the heat, wait a little bit of time and I look, my temperature is 11 degrees Celsius for the water, whereas my temperature of the sandy soil, that is up above 15 degrees Celsius. So water resisted a change in temperature more than the soil did. Okay, and I know that's kind of hard to understand, but the big idea here is the reason it resists change is because it can absorb that heat. It holds on to it. Okay, so it doesn't change the temperature that much. Why is this important? Well, because water can act as a moderator to regulate big temperature changes. So, for example, when you look at this map, okay, this is over on the West Coast here. If you look at the coastal areas, their temperatures stay relatively moderate as the temperature goes up during, the warmer seasons. But when you look a little further inland, whoa, 96, 106, I mean, that's crazy. Look how much warmer it is compared to the coastal area. The reason is because the oceans are able to absorb a lot of the heat and hold on to it, which means that the local area, the land here, is not going to be as affected by the temperature change. Okay? Also, within our own bodies, it's really good that we can moderate temperature. Think about the fact that you are constantly generating heat from all of the chemical reactions in your body. And what would happen if that heat wasn't absorbed by the water in your body? Why, your temperature would be off the charts. So lucky for us, because we're mostly made of water, the water can absorb all of the heat from those reactions, and that helps to keep our body temperature stable. Obviously, we have other mechanisms to further control our body temperature, but the fact that our bodies are made of 70% water really helps. It keeps that temperature stable. And the last property of water we want to talk about here is the fact that ice can float. So we want to talk about states of matter. You've learned in your previous classes about solid, liquid, and gas phases. Okay, and for most substances, the solid phase is most dense. Okay, but with water, it's a unique property here. Water is more dense as a liquid than it is as a solid, and that's because of the hydrogen bonds. So take a look at this diagram down here. Look at the liquid water. Each of these little red dots with the white dots attached to it, that represents a water molecule. You see how close the hydrogen bonds are between the water molecules? They're very condensed, and so we get more water molecules into the same amount of space. So that makes it heavier. Okay, it has a higher density. But when we look at ice, as water freezes, those bonds stretch from each other and they push each other away while still maintaining bonded. Now look at all this space that has occurred here. So this is the same number of water molecules as in the liquid water, but look at how far apart they are. They're more spacious. Because of all that extra space, the ice is going to weigh less, okay? It's going to have a lower density, and that is the reason why ice floats. So why is that important? Well, a majority of our Earth is covered in water, and a lot of the times there are seasons where we will receive freezing conditions. So why doesn't an entire lake, for example, freeze, during the winter? Well, the reason is because of the fact that when our lakes reach freezing temperatures, as water freezes, it floats to the surface. And then this creates sort of like a shield over the surface of the lake, right? When lakes freeze over like this, it stays very cold here, but that acts to insulate or keep warm the rest of the water. So that is why fish don't die in the winter and other marine organisms. They are able to live because the water is being insulated by that layer of ice that's on top. So the ice parts of water are going to float, and then the rest of the water underneath, the temperature is going to be a little bit warmer because of the insulating effect from that ice cap on top. The last thing we want to talk about is that water can break down itself too. In any substance, water can fall apart into two pieces. This side here, this is called a hydroxide ion. And this over here, this is a hydrogen ion. And we're going to focus on the hydrogen ions because the amount of hydrogen ions something has is a way that we measure its pH value. Okay, and I'm sure you've heard of pH before. Here's a picture of the scale. The pH value goes from 0 to 14. And right smack dab in the middle, a pH of 7 is pure water. So pure water has a complete balance in its hydrogen ion concentration. If you start adding more hydrogen ions to something, okay, like, looking at tomatoes here, then it becomes more acidic. So anything below 7 would be considered an acid. That is going to cause the pH number to go lower even though the hydrogen ion concentration is increasing, right? So here, when you look at this diagram, you see our hydrogen ion concentration here. Okay, notice the negative numbers on the powers of 10. So we're getting more hydrogen ions as we move this way on the pH scale. But look at the direction that we're going. Our pH value is decreasing as our hydrogen ion content increases. So something like your stomach acid or lemon juice, those are examples of acids. Okay? On the other end of the scale, if we go above 7, then they're going to have fewer hydrogen ions. So very low concentrations of hydrogen ions here, right? Because these are negative powers of 10, which means the number's getting smaller and smaller and smaller. Those are going to be bases or basic solutions. And a good example of that, baking soda or bleach. So it's important that you understand how we measure pH on a scale from 0 to 14. Each number represents the hydrogen ion concentration. And the relationship you want to get from this is that as the hydrogen ion concentration increases, the pH value goes down. The number goes down. So the highest that you can have hydrogen ion concentration will have a pH of 0. The lowest hydrogen ion concentration will have a pH of 14. Okay, so it's an inverse relationship. Okay, so that's the lecture on water. Again, make sure you check out those objectives, and if you have any questions, please feel free to ask in class.